We start now with explaining how multiplexers can be used for Boolean function implementation. We know that a multiplexer is really a decoder plus an OR gate from the way the multiplexer was implemented. Based on this fact, we can state that any multiplexer that has 2 to the n inputs and 1 output can be used to implement any Boolean function of n input variables. The variables are used as the selection lines, and 2 to the n are the data inputs, are used one for each minterm. Let us give you an example. We know that the full adder is implemented as follows. The sum function of the full adder is the sigma of the minterms 1, 2, 4, and 7. So, if we assume that the input variables of the adder are x, y, and z, then we can implement the sum function as follows. We can use x as the most significant selection variable, so it comes under input 2 of the selection, and y next, and then z. So these are the input variables that are used for the selection lines. Now how about the data inputs? The data inputs are as follows actually. We would like the minterms to be 1, so we put this 1 here, and 2 will be also 1, and 4 will be 1, and 7 will be 1. So these are the minterms of the sum function. So the other inputs will be zeros. So 0 will be to the input 0, 3, 5, and 6 of the multiplexer. Now what happens? If x, y, and z, as an example, take the value 0, 0, 1, then the input 1 will be channeled to the output, which will be the sum. Or if the input is 0, 1, 0 as an example, same thing exactly, the input 2 will be channeled, which is 1, and so forth until 1, 1, 1. However, a better solution is to implement any function of n plus 1 input variables. So instead of n variables here, we can use n plus 1 input variables, where n of these variables can be used for the selection line, whereas the remaining variable will be used for the inputs, as we will see next. This is an example to implement the function f of a, b, and c equals sigma 1, 2, 6, and 7. Well, let us assume that the function f of x, y, and z, instead of a, b, and c, it is the same actually. So we do it as follows. We divide the inputs, the 8 combinations of the inputs, into 4 different groups. Each group will contain 2 minterms. So we start with minterm 0 and 1, one group, 2 and 3, another group, 4 and 5, the third group, and 6 and 7. And then for each group, we express the function f in terms of the variable z, the least significant variable, as follows. Now, when the truth table for this function will have the minterms 1, 2, 6, and 7. So this will be 1 here, and 1 here for the 2, and the 6, and the 7. Now, if we look at the first pair of minterms or combinations, the function f, if z is 0, f is 0, and if z is 1, function is 1. So we can say that f is equal to z. And for the second pair, if z is 0, f is 1, and z is 1, f is 0. So we can say that f is equal to z prime. For the third pair, f is always 0. So we write f equal to 0. And for the fourth pair, f is always 1. So we write f is equal to 1. Now, to implement the function, all we need to do is to draw a multiplexer, and for the inputs 0, 1, 2, 3, we input z at the input 0, and z prime at the input 1, and 0 at the input 2, and 1 at the input 3. These are for the data inputs, and the selection variables, x will be for selection 1, y will be selection 0, where x is the most significant, as we can see here, and y is the least significant. And this is a complete implementation of the function. Let us verify our solution. Let's take any min term. Let's take the min term 6 as an example. 6 is 1, 1, 0. So 1, 1, 0, x is 1, and y is 1, and z is 0. So if z is 0, this will be 0, and this will be 1, and this is 0, and this is 1. So when this is 1, 1, the input 3 will be channeled to the output, and f will be 1, which is correct. Let's do a procedure, general procedure of how we can do this. We proceed as follows. First, we assign an ordering sequence of the input variables, and this we have stressed many times. The rightmost variable will be used for the input lines. As an example, if the function has 4 input variables, A, B, C, and D, D will be the least significant, and it will be used for the input lines. We assign the remaining n-1 variables, which in this case will be A, B, and C, to the selection lines with respect to their corresponding sequence. So A will be the most significant, C will be the least significant. We construct the truth table, and again, we consider a pair of consecutive min terms starting from min term 0. Then we determine the input lines. Let's take one more example, and then we conclude this part. Let us assume that the function of A, B, C, and D is the min terms 1, 3, 4, 11, 12, 13, 14, 15. We start with writing down the truth table. So we write the variables A, B, C, D at the left-hand side and write all the 16 combinations starting from 0, 0, 0, 0 to 1, 1, 1, 1. And then we write the value of f to be 1 for these min terms. So it will be 1 for 1, and 3, and 4, and 11, 12, 13, 14, 15 to match these here. The others, we write 0 in all other positions. So they will be 0 here, and here, and here, and so forth. Now, according to the procedure, we divide the combinations into pairs, starting with min term 0. So we have this pair here, the first pair, and second pair, and third pair, fourth, fifth, sixth, seventh, and this will be the 8th pair. Now for the first pair, we notice that f is equal to d, because if d is 0, f is 0, if d is 1, f is 1, so we write f is equal to d. For the second pair, same thing exactly, f is equal to d. For the third pair, f is equal to d prime, because when d is 0, f is 1, and when d is 1, f is 0. The fourth pair, f is always 0. Same thing for the next pair. And for the pair after that, f is equal to d. And for the last two pairs, f is equal to 1. Actually, having done this, we are almost done with the solution, because all we have to do is to apply the 3 selection variables, A, B, and C. We apply A to S2, which is the most significant bit to S2, and we apply B to selection line 1 and C to selection line 0s, and the data input will be taken from the truth table that we have just constructed. So for combinations 0 and 1 and 5, we input D. So this is D here, and D here, and D here. And for combination 2, we enter D prime. So we put here D prime. And then combinations 3 and 4, we enter 0. So we have 0 here and 0 here. And for combinations 6 and 7, this one and this one, we enter 1 here and we enter 1 here, and we get the output function f exactly as we want it to be. That is a really very simple way to implement any Boolean function using multiplexers. Thank you.